after all this work, what we try to also do is that create some kind of web-based interface. So recently, after creating the understanding of that, we have created a web-based information system which is called Manage. This website is publicly available. I mean, you can click on this particular website and it will give you all the information related to flood risks. Similarly, sometime when I was doing my postdoc in Canada in Western University, that time we derived the flood inundation maps for the entire of Canada. We developed the flood inundation maps for the entire of Canada for the historical time period and also for the future time period. And it was very interesting because previously Canada didn't have a flood inundation map. And once we created this kind of data like inventory, more than I would say 11 million visitors were there around the globe. In the context of Canada, we tried to create the flood inundation maps by understanding climate impacts, and this again was published in Science of Total Environment. Here we actually used a global flood model to understand the entire entire synergy of the impacts. For the first time, probably we considered the climate models from the CMIP 6 consortium, which is the most recently available. We considered around 17 different GCMs. And yeah, we try to understand how the flood intensity is going to vary. So I'm trying to show you, yeah, this one. We basically saw that the intensity is going to be very, very high. The frequency of occurrence is also going to be very high. Basically, the flood which were occurring maybe 1 in 100 years, they will be occurring 1 in every 25 years or 1 in every 50 years with the same degree of impacts. This is a very recent work that we have done. Right now we are talking about the importance of machine learning and artificial intelligence. And we also try to use some kind of standard machine learning models to derive the flood inundation maps. As an experiment, we tried to develop this framework for a very flood-prone catchment in Ganga Basin in India. It was just recently published in ESPR. And this is the entire framework where we are considering the digital elevation model. So in this particular work, we didn't run the flood model. We just considered the digital elevation model. The digital model, basically the topographic data, it gives a lot of other information also. Like for example, in the form of slope, elevation, the tangential feature. So a lot of indicators are there embedded within the topographic data, which will give us some idea about the existence of flood lines. Okay, so that is how we actually studied. We did some kind of training and testing based on an existing flood inundation map, and after that, we also did the Shapley analysis also. Basically, here you can see these indicators. Say for example, height above nearest drainage, downslope index, elevation, profile curvature. So basically, through the Shapley analysis, we can understand that which parameter is the most influencing on the flood inundation. So this kind of plot will actually give you that information. Final map is that when this is the existing flood inundation map of Ganga Basin, and this B is the map that we have derived. Many spots were there which actually were not shown as flooded or flood hazard in the existing map that we were able to find out. Say for example, here you can see this area in the top part of the basin. It is shown in red color, but actually by fitting the state of the art machine learning models, we found that these areas were not, they were kind of overshadowed. So we found out these areas were actually very high flood zone, and this is because if you don't know the exact information of flood hazard, then we are not having the exposure will be very, very high. We don't know what kind of flood measures also. You can also here you can see we also in the tail part of this basin. So this was the major, I would say, addition or major importance of considering the machine learning models, which gave us an idea that how this flood inundation hazard are existing, but unfortunately because maybe of hydrodynamic modeling, we are not able to find it out. And what we did was a case study in Bhutan. This is a very, very interesting work that we did. This is under, we have submitted this work recently, is that you all will agree that when we have a river, this is a river which is passing in Bhutan. The name of the river is Chamkarchu Basin, Chamkarchu River. Just near the Chamkarchu River, there is an airport in Bhutan. This is the domestic airport. And inside the domestic airport, we have a lot of entities, right? With the runway, the taxiway, terminal building, to tower. When we go to an airport, we also see starting going for security check-in or maybe collecting all the tickets, we see a lot of entities are there. Now, the problem here in this particular catchment is that this airport should not have been located near to a river, which is very much prone to flooding. You can see there's hardly any distance between the river and the airport. Now, what we try to understand, there is a very conventional outlook that we need to try and quantify the flood impacts entirely over this particular airport. But what we did is that something another interesting side is that how these entities are connected together. I think maybe you have taken the theoretical subject on construction planning and management, where we understand the strongest path methodology or critical path method. We try to utilize the same concept and try to implement on the airport. I mean, we know that if the runway is there, it is connected to the terminal tower. It is also connected to the control tower. So how the failure of one entity is connected to failure of another entity, try to understand the chain of impacts. That is what actually we did in this particular work. To assign some kind of weights, and finally we try to derive the interconnections between all these entities. You can see control tower is very much linked to the terminal. It is also very much highly linked to the runway. Try to understand the interconnections, and by understanding the we derived the risk indices. The last presentation is that which we are currently doing. This is a sponsored where we are trying to understand the impacts of flooding on the human health. Sometime during the COVID, also there was another important paper where they found that urban flooding is also posing risks of the spread of novel coronavirus during the pandemic period. We did some kind of study sometime in 2021, I would say, where in the same case study of Jagatsinghpur, we saw that the problem of flood was there. So that is the reason that people have to be shifted to cyclone shelters. But at the same time, there should not be any kind of huge population that is present in the cyclone shelter, because there will be huge contamination among the people. So what best we can do so that optimum number of people should be placed, and what distant they should be placed in the cyclone shelter, that is the work that we did. So it was published in ERL. But taking cue from that particular work, we thought of Delhi as a very important case study. Delhi has a lot of flood incidences during the peak monsoon time. You will hear a lot of news during the month of June, July, August. Just after that, you will hear another important news that there is a lot of outbreak of malaria or dengue. Okay, so what happens is that basically many areas which are not waterlogged, they actually get waterlogged during the peak monsoon time because of huge rainfall, widespread flooding, and because the waterlogging keeps on continuing, then they actually become the breeding places of mosquitoes or any disease carrying pathogens, and that is the reason we have a lot of communicable disease emerging from these localities. This is a framework that we have developed. The National Institute of Disaster Management also talks a lot about the water-related disasters, how it has implications on the health, human health, on the society health. So basically, this entire work consists of flood modeling. It also consists of capturing the data from the climate models, like let's say, for example, different RCPs and SSPs. And apart from that, we are trying to integrate the flood model with a water quality model, so that we can understand what is the water quality standards when the flood has already occurred post disaster, and from there, from the output of the like flood model come water quality model, we're going to get the human health risk parameter. At present, we have done some kind of rough study over Delhi, where we try to understand whether the urbanization and the rising rainfall extremes have actually led to the increase in the flood in Delhi, and actually we got positive results based on our hypothesis. This is the flood model setup for the entire Delhi, which was developed in 1D, 2D MicroPlus model. And very interesting picture, you can see that between 1993 and 2023, the urban built-up area has actually increased very, very high. And since this urban built-up area has increased, the amount of green fraction, or let's say the trees or vegetation, which can help us in reducing the flood depth, or let's say the flood momentum because of huge infiltration capacity, they have also synonymously decreased. This is clearly indicated in this index. Here you can see between 93 and 2023, the urban index has increased, right? You can see a clear exponential increase. Similar to that, you can see a very gradual, like huge decline in the greenness index. And these are the time periods when the flood events had occurred. We also modeled the 2023 flood event, and we had to contact a lot many organizations to get the data. Unfortunately, we could create a satisfactory flood inundation map, and this is the final picture where you can see this is the 2023 flood event for Delhi custody. This is the Yamuna River, and how the built-up area has increased. You can see 1993. These are certain spots. The built-up area has increased very, very largely, and because of this, actually, the amount of infiltration is actually getting declined. We have the amount of green fraction is actually declining, and because of which the runoff actually becomes much more prominent during any kind of extreme rainfall. So I think with this, I will end my presentation. I would like to again thank the committee of this particular ongoing program. Since thanks to NIT Patna, and I also would like to thank all the sponsors and funding organizations who have been a part and parcel of our research activities. You may reach out to me in these email IDs, mohit.mohanty@www.it.ac.in, and this is my Gmail ID. In case you would like to collaborate, you would like to discuss anything that is very much overlapping with the nature of work. So thanks one again. Thank you. Thanks a lot.
Thank you.
Professor Joseph, I hope that I'm on time because, or maybe if you want to take, ask me to take further time, I can take, or maybe you can open for any discussions or questions if they have any.
Yes, sir. So I request all the participants. So if you have any doubt or would like to ask question to our expert, it is open to you.
So I think Komal Vashist has some question, maybe.
Good afternoon, sir. Am I audible?
Yeah, Komal, you're audible.
Sir, it was a nice presentation. Just wanted to ask, what are the basic criteria to decide these, we can say, risk, hazard and vulnerability criteria for a specific areas?
Okay, so basically when we talk about hazard, if we talk about the deterministic aspect, we have to quantify the flood water levels, the velocity, and also the residence time of flood water. In India, unfortunately, we do not have any standards as such. If we talk about other countries like UK, Australia, United States, they have created some standards considering the flood depth, flood velocity. In India, probably you can see the regional, let's say, state disaster management authority papers. In our work, we had followed a criteria that was published sometime back for India. That was a standard that was based on the human height and how much impact it can have on the human height or the vehicles. Based on that, we had considered a standard that maybe you can find in our paper that was published in the Journal of Environmental Management. So that standard is present, which is a combination of your water depth, product of water depth and velocity. And according to that, we are saying whether it is high hazard, low hazard, moderate hazard, and as such.
Also, sir, there are no criteria that how many factors we want for that sensitivity analysis of risk analysis.
Factors can be many. I mean, when we talk about any flood model typical setup, there can be a lot of factors. And also it is very important to understand that the data has a lot of uncertainty as such, right? When you are using a flood model.
Yes, sir, exactly.
Yeah, whenever we are using a flood model, the model also has a bit of uncertainty, even though you are using the best, I would say, data sets. So it is very much important that first of all, we have to limit the uncertainty in the data. Otherwise, what will happen, let's say, for example, I'm considering a lot of factors. There will be some degree of uncertainty in this n number of factors. All this uncertainty might be added. That will be proliferated, or maybe it might shoot up whenever we are using them all in the flood model. But basically, I would say, like for any flood model, the basic parameters, which is topographic data, rainfall data, stream flow data, let's say land use, land cover, because you have to also take care of the Manning's roughness, tide data if you are staying, if that locality is in a tidal catchment. These data are primary. I mean, they should be considered. Apart from that, if you want to use, let's say, wind data or say infiltration capacity, all these things, if it is available and if it within the range, if they are creating the model stable, then it's okay. Otherwise, I think we have to create some assumptions and go ahead.
Thank you, sir.
Yes, anyone else? Right. Okay, Mohan is there, I think. He has text some question here. You can just check once.
Okay. Okay. How far the hydrodynamic modeling is suitable for urban flooding? Okay, so the hydrodynamic model for urban flooding, I mean, we did the flood analysis for the Mithi catchment in Mumbai and also for Delhi. See, first of all, for any model, be it hydrodynamic model or any kind of model, let's say we're using an instrument also, first of all, we have to calibrate and validate that. Okay, so we did that calibration and validation experiment properly or let's say comprehensively. And calibration, that means we consider some data sets in the past time period, we run the model, then we try to see whether our simulation is close to the results that was seen actually. Then again we try to validate for another event. By doing that, we limit that error term, right? So the flood model setup, we try to make it more and more stable by considering a lot of other computational factors. So for example, Coulomb number, which actually decides how the model is stable. When we create the model setup, we create a lot of grids, a lot of meshes, unstructured meshes. By I would say tuning all these factors, we first of all make the model stable. Once that model is stable, we need to do a proper calibration and validation. And by doing this, if we really find out that okay, the proper calibration validation is there, and then we realized that the results were okay. So that's how we have done for the Mithi catchment in Mumbai and also for the Delhi catchment. And we found out that by doing this model stability exercise, proper calibration and validation, we can get a proper idea of the hydrodynamic modeling of capturing the reality in the air. So yeah, I mean,
Sir, what is the model? Sir, what is the modeling accuracy in that sense? I mean, in that case, what you studied?
modeling accuracy, I mean, basically we found out the hotspots. We see, for example, when we talk about flood impacts, our major importance is that whether we are able to capture the high hazard spots, and that was more than let's say zero 0.7 something like that. We had some observed data for let's say for Chennai, we had some observed flood level marks. Overall, we can't say like because there may be certain locations where the maybe the error may be very high because the data itself it's bad. But overall, I mean, it is not right to say. But finally, we could find out like more than 0.6 or 0.7, which is a very good validation, I would say, for flooding. And most importantly, the high flood hazard spots, they were rightly captured. We actually want to capture the high water depths or high velocity. Those areas were rightly captured.
Thank you, sir.
There's another question by Divyashni Pandey. What are the different calibration parameters for urban flooding? For urban flooding or maybe for riverine flooding also, the first parameter is that of the Manning's roughness. So whenever we are going to create an urban flood model setup, we also have to create a network of the man-made drainage systems. So in that case, we have to take care what should be the optimum Manning's roughness coefficient. Similarly, if we are talking about a riverine catchment, the Manning's roughness is more associated to the river channel bed form. So that time also we have to tune that particular Manning's in. There can be also Manning's n for the overland parameters because vegetation has a different Manning's n, built-up area has a different Manning's n, open land can have a different Manning's n. So preferably we try to tune the Manning's coefficient. Then only we will get a good accuracy in terms of simulation and the observed data.
Hello.
Yeah. Yes, madam.
So, for coastal flood modeling, so what are the parameters we need to include for the coastal? What are the parameters which influences the flood? So, because the flood from the urban, it reaches the coast. No. So, what parameters which impacts the either? So, both the ways it affects. One is the seashore or the coastal, and also the urban. So, how do we couple, or what are the parameters are important for that?
Yeah. I mean, for the coastal case study, the first point will be the coastal ocean. So basically, we have two different things. One is a very dynamic component, which is the tidal part. We term this as storm tide. Tide actually happens to be a more or less, like let's say, stable form for almost 17 to 18 years. But during the time of local depressions or cyclone activity, when the wind is associated, then that tide head actually also increases. That is what happened in Mumbai flood also, where the tide height was around 5.3 meters. So we term this as storm tide. That means tide is a very much, I would say, usual component that happens. There is a usual tide level for every catchment, every coastal region in India. But because of the cyclonic depression, there might be an increase in the height that is known as storm or surge. If you add both of these, that is known as a storm tide. And the other component that we not often talk about, because that is going to happen maybe after 40 years, 100 years, is the sea level rise. That is more or less not a very dynamic component, but when we create the flood model, if we also identify on or maybe input the sea level rise also, that along with the storm tide data, because storm tide data is more dynamic, it is going to enter from the sea or the water body towards the landmass through the mouth of the river, or maybe it will have some kind of impact on the landmass that is just connected to the river, just connected to the landmass. But sea level rise will be a more or less a standard phenomenon of creating some subsidence. And apart from that, if we are more concerned, also rainfall because the inland rainfall will lead to runoff. That water will try to go from the land towards the sea. That is also an important. So basically, pluvial flooding related to the precipitation, then storm tide and sea level rise.
Sir, how do we get the data for the storm? How do we get the data for the coastal flood modeling? The parameters, what you said is the tides and the waves. How do we get where is the data available for that? So how do we get?
So there are tidal buoys, which are basically the instrument that are kept in the water source that collect the data. So the nodal organization similar to like Central Water Commission that gives us the data for the water level in India. IMD gives us the data for rainfall. So INCOIS actually gives us the data for the tide related thing. So they have installed a lot of tidal buoys in many parts in the eastern and western part of India. You may contact INCOIS in an official manner, what kind of data we actually require for which tidal buoy. Based on that data availability, they might give you. And also, if you can visit to any inland port authorities, they also have their own inbuilt tidal buoys because they need to understand what is the rise in the water level so that the ships or the buoys can be transferred. So they also collect a lot of data, maybe, but that may be classified because that is used for their purpose. If at all you have some kind of, let's say, project or consultancy with them, they might share. But otherwise, the nodal data which covers the data is INCOIS.
Thank you, sir.
So anyone else? Okay, sir. Thank you. Thank you very much, sir, for your time and consideration. It was a very nice presentation. So in future, we'll meet again if time permits. And yes, I also thanks to all the participants for your patience. So we'll start again next section within few minutes. Okay,
Please
thank you,
share
sir.
mail ID, sir.
Yeah.
Thank you.
Yes, sir. You can.
Once again, thanks, Professor Joseph and Professor Bhavani, so for giving me this opportunity. It was very nice to interact with all the participants, share whatever we have done in the current time. So thanks a lot. Hope to see you soon again, and best wishes again for your
Sure,
event.
sir. Okay.
Thank you. So I can sign out then right now.
Yes, please, sir.
Thank you. Thanks a lot. Thank you.
Thank you, sir. Am I audible?
Yes, sir, you are audible.
Abhishek sir, you are muted, sir.
Okay, I'm muted.
Abhishek sir, can you please unmute yourself?
Can you hear me?
Yes, sir.
Yes, sir.
Okay. Voice is clear?
Yes, sir.
Okay. Thank you.
Dear participants, am I
Yes, we can start, sir. Can you hear me, sir?
Yes, I can hear you. I think my voice is not audible to. My voice is audible?
Let me put my fan off.
Yes, sir.
Okay, sir. Okay. So, Professor Abhishek sir has already delivered a lecture yesterday, and it was a very nice lecture. So, today we'll be again hearing one more good lecture from sir. The topic is challenging in reproducing the fluvial bed forms using the 3D CFD models. So thank you, sir, once again for your time. Sir, time is yours. You may start.
Okay. Thank you, Professor Joseph, and I will start my lecture for today's session. Before that, I would like to put a request for all of you that I want to make it very interactive session. So please ask as much question as you can. So you can interrupt me in between while presenting the lecture, and feel free to ask any question, even if you are in first year of MTech, first year of thesis, PhD, and if you feel that you are unaware of these terms, you can please feel free to ask me, because these are designed to impart some knowledge. So just don't listen the entire thing. Please interrupt and please ask as many questions as you can. So now I will share my slide, and slide I have again made it very crisp. I can't put all the details in slides. So if you need any extra knowledge, if you need any additional information, you can definitely ask me. Right. So I hope you can see the slide, right? Can you see it? Anyone can confirm?
Yes, sir. It is visible.
Okay, nice. So for today's lecture, I have chosen the topic challenges in reproducing the fluvial bed forms using the 3D CFD models, and the insights are from the channel junction simulation. Actually, channel junction simulation was part of my PhD thesis, and as well as my postdoctoral work. So the insights are mostly from the channel junction simulation, and you can also refer to other fluvial system. Channel junctions you provides very unique features in terms of the flow features and characteristic bed forms. Therefore, I have chosen this topic for today's lecture. So as I have introduced a lot about the junction flow, here again I will try to repeat those things. Yeah. So in tomorrow in yesterday's class, I have demonstrated the different flow features at the junction. This is the very simplified definition sketch of the junction flow, where you can see when two flow meets, there is a formation of the stagnation zone where the flow velocity is minimal, flow velocity is very low. The formation of the flow separation zone, which is primarily because of the this sharp corner, which may not be the case in the natural river, or even if it is, the extent of the flow separation will be very limited. You can see here the this mixing interface, because the velocity of the two incoming flows are different. So when they mix, there is a formation of the mixing interface, which is a source of different varieties of vortices. Similarly, here you can find multiple mixing layers because of differences in the velocities. So these are the characteristics flow features, means that these flow features are very general, and you can find them in the wide range of the confluence problem. So depend on the different parameters like the flow conditions that you are imposing on the two channels, and the junction angle and the junction plane form. This will govern the shape, size, and other features of this flow. So now, having said this, the characteristics flow features will have a feedback on the bed of the junction bed. So junction bed have also a very characteristics flow features. You can see here when two flow interacts here, there is a formation of the scour hole here. This is called mid-channel scour hole. Why this is formed? This is formed because when the two flow meets here, so you see here there is a formation of the flow separation zone. Because of this, the available width is not decreased. Only this much width is now available for the passage of the flow. The quantity has not increased, but the width has decreased. Therefore, the flow velocity will increase in this region, and that is called maximum velocity zone. So here the flow velocity will increase. Because of the increase in the velocity, you will find the increase in the bed shear stress. And the bed shear stress causes the erosion in this at this location. So this is called mid-channel scour hole. That's because of the formation of the maximum velocity zone. And maximum velocity zone is formed because of the formation of because of the contracted flow. The flow is not contracted. So what I mean to say here, say here that when Q1 and Q2 interacts here, the available width is now contracted. The width is now partially covered by the flow separation zone, and therefore the available width for the passage of the flow in the downstream is now limited, and therefore the velocity is increased, and that causes the increase in the bed shear stress, and thus you see here the formation of the scour hole, mid-channel scour hole. Now you see here another scour hole here, but that's because of this sharp corner of the confluence. So when we model the confluence of the experiment in our lab setup, generally we have a flume. So in that flume we have sharp corner, right? So because of the sharp corner, it is formation of this cover. That is called local cover. Now you see here multiple bar. I mean, you may find even more than 2 bars, but because the experiments are very limited and the extent of the experiments are limited, so here I have demonstrated only 2 bars. So here you find 2 bars. The bar is deposition bar. So meaning thereby the flow the sediments are now here deposited settled. Therefore, there is a formation of the bar here. So why this bar is formed? So you see here again the flow feature. So when there is a doubt, when there is a characteristics flow features, you have to understand the flow features. When there is a characteristics bed feature, you have to understand the flow features. So see here, you can see here the flow separation zone formation. What is the flow separation zone? It's actually the zone of low velocity that's oriented towards the upstream in this case. So when the flow separation zone is formed, here there is a formation of the recirculation zone. That's what it does. It actually help the sediment particle settle on the bed. So when there is element of the particles on the bed, the bar will form. So because of this flow separation zone and secondary current, so I haven't shown here secondary current, but I will show you. So when the tributary flow interacts with the main channel, because of the curvature, it tries to bend towards the tributary again, and in doing so, there is a formation of the strong secondary currents. So because of the secondary currents, the sediment is not transported in this zone, and therefore you see here the formation of the deposition bar, which is aligned along the flow separation zone. So now here I have demonstrated the characteristics flow features and how these flow features are related to the specific flow, characteristic. Here I have demonstrated the characteristics bed features and how these bed features are related to the specific flow features. So actually the flow feature and bed features, they are interrelated and they will govern the formation and evolution of each other. So we will try to understand here the relation between the bed and flow evolution. So for that purpose, we will use 3D simulation, and we will discuss the challenges that we will face in doing so. What are the limitations of the 3D model in reproducing the bed features? What are the and the possible application of the CFD in reproducing the bed features? So here the bed feature means I am repeatedly telling the story of the channel junction, which has the characteristics bed features means it has cover hole, it has deposition bar. So can the model simulate these things, these features satisfactorily? Satisfactorily means here that you can accept the outcome of your model based on the engineering application. So that we will try to understand that the model that we have, can we use that model to reproduce these things, this cover hole and deposition bar? If yes, to what extent, and what are the challenges, what are the bigger challenges, and what are the limitations, and what we can do in the future to improve the results, improve the outcome of the 3D model. So these are the content that I will share in today's lecture. So this is from the experimental setup. So the experiments results are from Yu et al. So they have conducted experiments and they have generalized the flow features and the bed features at the junction. So having said this, now we'll move towards the numerical model that we will try to employ for reproducing the bed feature at junction. So here the objective is, again I have said this, studying bed topography and flow evolution at the channel junction, utilizing the 3D CFD modeling, applicability and their limitations. That is the topic for today's lecture. Right. So in yesterday's class I have discussed the CFD modeling, but that's for the rigid bed case. There is no bed deformation in the earlier case. So only I was discussing about the hydrodynamic model. Like I have used RANS model and supplemented with turbulence model and VOF model. In this case, there is another model that you have to work, that there is a scour process occurring at the bed, right? So we have to do the model of the flow and model of the bed. Bed means here the bed is here the pack of sediment particles, right? So we have to employ two models in the 3D CFD model. First one is called hydrodynamic model, that is written here. So for hydrodynamic model, similar to the earlier one, we will use 3D RANS model. We can use many other models like LES model, DES model, or sometimes we use 2D model. So 3D models are time consuming, resource consuming, and sometimes it doesn't provide better results. So instead of going for the 3D model, generally those who are working in the area of river engineering, they prefer to choose 2D model because they are less time consuming. So now, but here I have chosen the 3D model because in yesterday class I have shown you how the junction hydraulics is very complex and it's not possible to use, it's not judicious to use 2D model because of the complex flow nature, and I have also shown you the results of the various flow features that the course it's a 2D model also. So now here for hydrodynamic purpose, for hydrodynamic modeling, 3D RANS model has been chosen, and this model and the 3D RANS model needs some turbulence closure because if you have idea of the RANS equations, you will get to know that there are some unknown terms in the actual RANS equations which needs to be closed, and for that purpose we need some extra equations, and therefore we need that turbulence model provided those extra equations, and there are various turbulence model that you have to choose the base model for you. Again, if you choose any model, no turbulence model is perfect. Even if you choose the most sophisticated model, it will give you the bad, it may give you the bad result. But that's not the things you need to worry because the model has certain limitations. The model has been developed for simplified flow. It has been validated for simplified flow. So when anyone has a question? Okay. So all the models are imperfect in the sense they could not, they cannot provide you the accurate results for all the flow features, but still you have to make a compromise because based on your choice, based on your interest, you have to choose one of them, and you choose the model which is best fit for your case. So to understand which model is best for your case, you have to do some simulations more. For example, if there are 5 turbulence model, 6 turbulence model, and which one is better for you, so you have to take a call. For that purpose, you have to test the result from all the turbulence closure, and then you have to match them with your experimental data, and then you will make a conclusion that this model for your case at hand makes more sense, makes more satisfactory results. So that's up to you. That's your call that which turbulence models will be chosen. So for the, and most important thing is that the time and resource constraint. So for example, if you choose some very sophisticated model, it may give you better result, but sometimes it's not possible to provide so much time and money for that computational purpose. So for the current study, I have chosen the RNG capsule model. You can search for the term, you can read as much as possible for all this turbulence model. You can refer any standard textbook on turbulence model. You can read the papers concerning the CFD modeling, and then you will learn what are the applications and limitations of various turbulence model. So for today's work, I have chosen the RNG K epsilon model. So it's a variant of K epsilon turbulence group, and the choice has been done based on a comparison that I will show you in the next slide. Again, that's a water and airflow. That's a multi-phase flow, and for that purpose, I have chosen the volume of fluid method for computing the water surface elevation in our simulation. And these are the other bullet points like simple algorithm. That's the name of the algorithm that is used for the coupling of the velocity and pressure, and the types of discretization, and again time step size is based on the Courant stability condition for the case. These things you need, or if you know it's better, if you have any doubt you can ask me, or you need to read some good papers, some standard textbook to understand these terms. Now, having said this, that I have used the RANS model supplemented with the RNG K epsilon turbulence closure. So, why this turbulence model I have chosen? So, for the prediction of bed features, it's always you have to ensure that flow field is correct, simulated correctly. If the flow field is not predicted satisfactorily, you can't predict the bed features. So, RNG turbulence model is effective or not? Is it capable in reproducing the flow features at the junction or not? If yes, then we can choose this model. Otherwise, we have to choose the other one. So here I have chosen three model. So I have chosen here. I have chosen two model, RNG model and RNG K epsilon model and simulated LES model. So LES is very sophisticated model, and it provides, of course, better results. That theoretically, it provides better results. And when you use LES model, it's a very time consuming. It takes, even if, for example, if you give 7 days for one simulation, in case of the RANS modeling, you have to give around 100 days for the LES modeling. I mean, based on your computational facility also. So here I have compared the flow field. The flow field means here the contours of the velocity, contours of the longitudinal velocity. That's the velocity along the x-axis with the experimental data and simulated results from the RNG turbulence model and LES model. Now you see here the flow is very complex. You see here the maximum velocity zone here. The maximum velocity zone has maximum magnitude here, and there is a formation of the flow separation zone here. That you can see because the experimental data are limited, so the formation of the recirculation zone here is limited, but still you can recognize, you can discern that there is a formation of the recirculation zone here. And similarly, when the flow is simulated using the numerical model, similar to the experimental values, there is a formation of the flow separation zone in both the turbulence model, like RNG model and LES model. But you see here that the extent of the maximum velocity zone is overestimated by both the model. In experimental data, the zone of the maximum velocity is limited, but in simulated cases, the zone of the maximum velocity is rather, I mean, it's a very it's a longer than the experimental one. But that's a flaws that flaws are present with both the model. Even if you use LES model, you can see here the zone of the maximum velocity is overestimated. But you see here, the velocity recirculation zone is almost predicted nearly same by the LES and RNG model, and it does not provide any improvement over the RNG model. So LES model, being the sophisticated and being the time consuming, resource consuming, it does not provide very much improvement over the RNG model. So if it does not provide very significant improvement, and since it's time consuming, we will not choose the LES model. You can do that, but since I do not observe any significant improvement over the RNG model, so I will go with the RNG K epsilon turbulence model. So that I demonstrated here the choice that I made based on the logic between the logic arising from the comparison of experimental and simulated results from both the model, means RNG model and LES model. So now it's clear why I have chosen the RNG model. Now I will go to the sediment discover model. So till now I have discussed about the aerodynamic model that concerns with the flow of the water. Now what is the story occurring at the bed level, and how can we mathematically formulate those phenomena, those physics that occurring at the bed level. So bed is assumed as the packed sediment, right? And the sediment can be in both two mode. Sediment can flow in forms of the bed load, and it can also be in the suspended load. So when so we have to model two things: bed load and suspended load. Another thing is that, so when there is a turbulence at the bed level, so because of the turbulence, the bed particles are injected in the flow. So we have to model those things. Similarly, because of the gravity, the flow settles. We have to model them also. But two things here. Third thing, the concentration of the suspended sediment in the domain. And fourth one is we must compute the bed load transport load. If we can do these four things mathematically, then we can compute the changes in the bed level, because that's the problem of the continuity. So mass will be conserved also, will be conserved always. So if there is a bed and the flow is occurring over the bed, if we can somehow mathematically modeling how the flow, how much the bed materials is going in the flow, how much is going, how much settling from the flow, and how much bed load is coming from the upstream, and how much bed load is going in the downstream. If we can do somehow using some empirical formulae, using some physics-based, physics-driven method, then we can somehow estimate the erosion rate, and then from the continuity of the continuity of the mass, we can estimate the changes in the bed level. So that's what we are doing in this study. So for computing the bed load transport, there is a well-known empirical equations. Empirical equations mean they are developed under certain conditions using set of experiments or numerical simulation of observations. So they are not entirely physics-driven model. They are developed based on strong observation and some theoretical framework. So you see here, I have chosen here Mayer, Peter, and Muller equation. So that's a known by name MPM, and that is the empirical equations of the MPM that computes the bed load transport, and the tau star is that's the bed shear stress that causes by the flow on the bed. So the shear stress, the stirring mark denotes the non-dimensional number. So if I remove this non-stirring, this star over the tau, so it means that bed shear stress because of the flowing water over the bed. And the tau C denotes the threshold condition for which you will observe the incipient motion. For example, the flow is occurring over the bed. So the flow will exert some bed shear stress on the bed. The flow will exert the shear stress on the bed because of the gradient of the velocity. So here you see that, yeah. So when the bed shear stress exceeds certain limit, then the bed particle will start moving in the channel. So that is a threshold value that's known as a very popular name shield parameter, right? So here the shield parameter is 0.035 and 0.053 because I have chosen two cases. So there are two experimental data sets from different authors, and the materials size are different. So I have used here D50. So theoretically, the river bed is composed of varieties of particles. You will have a grain size distribution, but for numerical model, the case is simplified, and the entire bed is represented by D50. That's a major drawback of the numerical model. Of course, you can use of course, you can use various layers of different bed materials, but for simplified case, D50 is taken and it represents the entire bed of the channel junction. And from D50, you can calculate the tau C star from the shield from the curve that gives you the particle Reynolds number and shield parameter curve, right? So from that you can start. You can choose the value of tau C star from if you know the D50 value. So this is the how we will calculate the bed load, sediment bed load, and for the concentration of the sediment suspended particle, we will use convection diffusion equation. I will show you the here the mathematical formulation for them. So here. So that paper is published now. So yeah. So here you can see this is the equation of that's a convection diffusion equation, and that's used for the computing the concentration of the suspended particle in the water flow. Now, having said this, now there are two terms more left. The first is settling of the particle. So what is the rate of settling of the particle and how the particle is going in the flow due to the local turbulence. So for that purpose, there are, that's a physics. We need a better understanding of the sediment transport to model these things. But unfortunately, the progress is not up to that mark, and therefore we generally use empirical equations instead of the physics-driven model. So here you see here there is the formula of the lift velocity. That's a velocity that comes from the bed particle to the flow, and these are entirely empirical equations, but of course in the framework of some theoretical knowledge also. And similarly, you see here how much the suspended sediment will settle on the bed by using this formula of the settling velocity. So we could now able to model those things: the settlement, the entrainment, and suspended concentration, and the bed load transport. So we could model somehow these parameters using the numerical model. Then we will use the Axner equation. That Axner equation is actually a conservation of mass of the bed particle, and that will tell you the changes in the elevation of the bed. So if you calculate how much sediment particles are entraining in the fluid from the bed, how much settling from the flow to bed, and how much sediment, what is the rate of the bed load transport, by that we could model the bed elevation using this formula that's called Axner equation, Axner continuity equation. So this was the story of the numerical setup that is used for the SCOVER modeling. And one more thing parameter is here, porosity, because sediment particles, of course they are packed, but there may be, of course there have to be certain porosity, and that's what here you can see the porosity values is the value of porosity is taken 0.4. You have to calibrate those values for your specific case, or you can start with some standard values of 0.4, 0.38, 0.42 and see what gives the better result. Right. Having said this, now this was the story of the numerical setup. Now we will move to the computational domain. So I have chosen two computational setup. So this one is from the experiment of Yu et al, and this one is from the experiment of Nazari and Gilou et al. So here the idea is that in the first case, only equilibrium bed conditions are given, but in second case, you will find that the bed evolutions are also given at different time stages. So to test the model holistically, to test the model in more wider sense, it is validated not with the equilibrium condition, but with also the evolution of the bed at different time stages. So therefore, I have chosen two different experimental setup, and you see here that's computational domain, and this gray shading shows the bed that's going to be deformed in this case. And that's the extent of the mobile bed that's going to be deformed in this case, and the layout of the mesh, the cross-sectional view, the plan view for both the cases, and this gray shading shows the inaudible bed again with the D50 of 0.32 mm and D50 of 1 mm in the in the other case. Right. So now we will impose the boundary conditions on both the model. So again, the boundary condition that I will impose here, the velocity inlet, and water depth. And the velocity inlet and the water depth comes from the experimental values. So for example, in the experiment, the discharge is 9.6 liter per second. So I have to specify them in terms of velocity and depth. Similarly, at outflow, the tail water depth is specified from that these values comes from the experimental setup. And at walls, no slip boundary conditions and the standard wall function was imposed. At top, symmetry boundary condition is imposed. If you have any queries regarding the boundary conditions, you can ask here. So now these are the setup of the numerical model. Now again, now we will test where we will assess how much the model is successful in replicating the bed surfaces. So you see here by the contour plots, this is the contour plots of the bed elevation. That's from the experimental results of the Yu et al. And the results correspond to the equilibrium bed conditions, means there is no significant scour and deposition phenomena once the bed achieves the equilibrium condition. So here you see the formation of the scour zone, the formation of the deposition bar, and there is also formation of the bar, the fan shape deposition here also. So this is the experimental results. Now this is the simulated results. You see here, the qualitatively we can see the matching is satisfactorily, but the quantitatively we are we are not much successful. The results are matching qualitatively, but you see here the extent of the separation zone, the orientation of the separation zone is not matching perfectly. And we will discuss what are the reasons, what could be the probable reason that we could not do that. And that is challenges we will discuss in today's class. And here you see the deposition zone is here like point instead of bar, but here in the case you see here, it's a kind of elongated bar here. But still, you can see here the numerical model could predict the separation, the scour zone in the mid confluence region and the deposition bar in the separation zone area. So for with the R square value 0.648, not bad, of course not good either. So now the question is. So the comparison was using the contour map. For better representation, I have taken the bed values, the elevation values at two different cross sections, and these two different cross sections are located downstream of the junction at 0.05 meter and 0.10 meter. So these two cross sections are located downstream of the junction, and you see here the comparison of bed surface of bed elevations with experimental data. You see here again the results are satisfactorily for the engineering application, in the sense that we could predict the maximum scour zone. We could predict, for example, the value of the maximum scour zone is 0.0452 meter, and similarly here 0.046 meter. So the maximum scour value is now predicted satisfactorily, but the entire region of the scour is not predicted satisfactorily. So while we can use the model for the engineering purposes, for the design purpose, but for the physics purpose, to understand how the flow and beds are interrelated and how there is a feedback mechanism between the bed and flow, there are still gray areas, and the results may not be considered satisfactorily from that perspective. But what could be the reason? The reason that we will discuss, because the 3D model has lots of uncertainty, and because of those uncertainty, we are seeing the mismatch despite the considerable effort. So now here you see that the match between the experimental data and simulated results, that the maximum discover values are predicted satisfactorily by the numerical model. But here there is a mismatch, here there is a mismatch, here there is a mismatch. So these things comes from the various uncertainties, various limitations, and we will of course discuss those things. Right. Now that was the, now I have shown you that results using the MPM equation. So I have tried using the different bed load transport equation. So there are another equation called Van-Ryn equation. You might have heard of this bed load transport equation, and it's a very popular, similar to the MPM equation and Nelson formula. So I have used these two bed load transport equation as well to see if there is any improvement in predicting the bed elevations. So, but unfortunately, you see here the prediction is not very motivating. It doesn't give any better improvement over the MPM method, and therefore these two methods are abandoned here. And from the literature, if you see here, MPM method is very popular and people generally use MPM method. They are well tested. I'm not saying that these two methods are bad. Many people have used these two methods very, across the different hydraulic problems. But for this case, MPM method suits better for the given problem at hand. So further simulations are done using the MPM method only. So here just the purpose was to show that if there could be any improvement in the if I use the Van-Ryn method, Nelson method instead of the MPM method. But unfortunately, the results were not interesting, were not motivating, and therefore we could not find any huge improvement over the MPM method. Now you see here the velocity field, that is but we will discuss these things later. So here now again, so for the since we validate the model with the bed elevations, now we can also model the values of, we can also validate our model with the velocity data. So at two different locations, x is equal to 0.1 meter and 0.2 meter, the velocity along the cross section of the river, along the width of the river, you see here the experimental values of u and v. You do not see the longitudinal velocity, and v do not see the velocity along the channel width of the main channel. So you see here the match cannot be said perfect, but however it can be said satisfactory. Since the bed topography could not match, so if the bed topography could not match satisfactorily, it's obvious that velocity field will not match satisfactorily. And the same, and the vice versa. If the velocity field is not matching, the bed topography may not also match, because there is a strong link between these. If to know if it could predict the bed elevations at different time stages at naught. So for that purpose, here the experimental results from the test case 2 was compared with the simulated data. So you see here the bed elevations at different time instant. For example, it's for 10 minutes or 20 minutes of. So give me a couple of minutes. It's yeah, so the bed elevations are compared with the simulated data at different time instant of time t is equal to 10 minutes, t is equal to 20 minutes, t is equal to 40 minutes, t is equal to 90 minutes. What you see here, that right from the beginning, the qualitatively, again, the qualitatively the results are matching, but quantitatively the results are not matching. They can't be said perfect, or they can't be even said satisfactory, but yes, they could predict the maximum discover value at different time stages, and the pattern and the formation of the discover zone at later time instant, they can be said to be similar. For example, if you see the results, the comparison of the bed elevation at time is equal to 90 minutes, you see here the qualitatively the geometry of the discover region can be said to be can be said to be matched with the experimental values. So this portion, so this shows the simulated results and this shows the experimental values. But at initial stages, the results are more, the simulated values are more far from the experimental data in terms of the geometry of the discover. But again, at all time stages, the discover position and the values of discover, the maximum values of discover zone is predicted satisfactorily. So here we demonstrated that not only the equilibrium bed condition, the bed topography could also reproduce the bed features at different time stages. There were some certain limitations, of course, there were certain mismatch also that we discussed. Now we will discuss what could be the source of the mismatch, what could be the source of mismatch. So see first, so when we do experiments, what we have the sand bed that's made of different particles, right? And these particles are represented by here only by D50. That's a major drawback of the study. Second, we have used the hydrodynamic model that uses the turbulence closure. So turbulence closure is not a perfect modeling of any flow simulation. When you do a turbulence model, you just could not simulate the flow in vortices perfectly, and therefore it could not predict the flow separation perfectly, and that was reflected that why the bed morphology could not be simulated perfectly. Again, and the other thing was that there are lots of parameters in the model. For example, the shield parameter, roughness values. These values are highly uncertain and very difficult to estimate, and therefore because of these uncertainties and limitation, we have the limited outcome from the 3D model, and but still we can use this model to reproduce the complex flow feature for the engineering perspective. If you go for the research perspective to understand how the flow and bed are, there is a role between the bed and flow and how they are in a loop, and I mean what is the feedback loop between them and on the interaction between the bed and flow, there could be certain challenges as well. So here you see the plot of the secondary currents and the shear stress. So here you see here there's a cross section, and the cross section is located at the downstream of the junction. You see here at time t is equal to 0 when there was no erosion, the shear stress was very high, and that shows the secondary currents. And the secondary current that you see here, the flow forms here a vortex. Here is a vortices that's called cell. So then you will observe this cell at the different time stages as well. So this cell is, the size of the cell is increasing. You see here, that's called secondary currents, and that's called the helical cell from secondary currents. And you see here how these secondary currents is pushing the bed materials from the mid channel to the side of the channel, and because of this there is a formation of the deposition bar here. You see gradually a different time instant from the time t is equal to 0 to equilibrium condition. You see here how the shear stress is increasing and decreasing, and how the separation zone, how the deposition bar is formed and how the discovered region is formed. And because of this secondary currents, you will also notice the changes in the so this is the plot of the Horso vortices. So here you see this is called Horso vortex. That's here kind of helical cell that you could observe here. So you could observe here the helical cell. Similarly, if you see the different cross section, then you can understand how this helical cell is formed at the junction. So this helical cell is very important for the incipient motion, but since the model is using Rand's model, we cannot comment much on the role of the helical sail in the incipient motion. Had we done LES model or DNS model, that's not very easy. It requires lot of time and resources, and sometimes even beyond the scope of the study. So then we could be able in the better position to understand what is the role of the helical sail in the incipient motion at the channel. And similarly, you see here the flow separation zone that's formed at time t is equal to 0, but at equilibrium condition when the flow bed is deformed, it decreased considerably. The size has not decreased considerably. It's because you see here when there is a secondary current is formed, it actually gives the momentum to the separation zone. When it provides the momentum to the separation zone, it actually gives the energy to overcome the adverse pressure gradient, and therefore the separation zone is limited in this case when the bed is deformed. So here the takeaway is that when the bed is deformed, the separation zone is reduced considerably in this case. Now, this was the conclusion, and limitations are that, again, the limitations are with if you want to conclude the findings, the limitations are with the numerical model and with the simplification of the simplification with the confluence geometry also. So that was the story of the today class, and I hope that you have enjoyed it, and please ask some questions or suggestion, comment, all things are welcome.
Thank you very much. Thank you very much, sir, for the lecture. So I request participant to ask questions if they have any doubt. So time is yours. Yes, Mohan, please ask.
Sir, what are the specific merits to use 2D modeling instead of being used 3D modeling?
So your voice is breaking. I could not hear you.
Go for 2D modeling only.
Yes.
Sir, if I want to use 2D modeling,
yes,
especially in the case of hydrodynamics, what are the specific merits?
Merits or demerits?
Sir, am I audible, sir?
Yeah, I can hear you. Please ask your question.
Sir, while going for 2D modeling, in the case of hydrodynamics, what are the specific merits?
So see, the merit of the 2D modeling is that it's a simplified approach and it takes less time while giving you the almost not entirely but almost most of the important bed features of the flow features. That's a merit. So in less with less resources, you can do that 2D modeling. 3D requires much more timing and resources.
Thank you, sir.
Anyone else? So if you could not ask directly, you may text also if you have any doubt.
Yes, if you have any email, I mean, if you have any doubt, you can uh, put your question here also.
Okay, sir. I think there is no question from there. So thank you very much, sir. Once
Thank
again,
you.
for giving us a very wonderful presentations. And soon in future we'll meet again. So I also thanks to all the participants for your patience throughout this session. So we'll end this for today. Thank you, sir. Thank you, sir, again. Once
Thank you.
again.
Thank you. Oh, thank you.